record. And so studies at 13, one more, only one more study set. Can you believe it? My other class had their last study set. They have a final, so. All right, so these charts hopefully are becoming a little bit better. And so to figure out for CO, we'd want to compare 1 to 3. And you need to be careful on this one because the exponent, right? So this is doubling. So when we doubled CO, the rate did double. So that would mean it's first order for the CO. And then to figure out for the NO2, we'd look, I'm going to go from 2 to 1. So the CO doesn't change, but I doubled there, and in this direction it doubles. So it's first order for both of them. So we would just write the rate equals, K. Don't forget to write K. The rate laws always have a K there, and CO times NO2. All right. Zero order would be that the rate would not change. And then second order, we've seen those. There are, again, I've mentioned other possibilities. I'm not going to, I try to avoid those kind of curveballs where you would get a negative exponent. There are ways to figure it out where you do log functions, but if you decide to go into this kind of field, you can work with that. Right, so we would just plug in the first set of data, so 3.4 e to negative 8 molarity per hour. Whatever the units are, you just go with it, and then we divide by our CO, 0.005 molar, or moles per liter, and the 0.00036. And you should get my answer. So one of the molarities cancel, so the units this time are just m to the -1, h to the -1. Or you can write per molarity hours. All right, and then the initial rate for experiment 4, and that is actually a just the correct way of saying it. It is actually technically called the initial rate rather than rate, but I just say rate. And so we would just plug our numbers in to our rate law. So the rate equals, you want to plug the K in. And please show units. Most of you did that. And respect sig figs. So we just plug our numbers in. I wonder why they wrote the exponents like that. All right, and you'll get this answer. All right, and then on number 5, again, it was one big study set, and so I've split the study sets into 2 pieces, so that it was, because you guys, I've learned this class 222 all the time, no matter for 20 some years, you guys always wait until the day it's due, and so then it was like a 3-hour homework set, and when I split it in half, they're each 1 hour, so it takes less time for some reason. Can think about that. So this is the natural log. We know the half-life. Yeah. So natural log of 1/2 equals negative k t 1/2. We do that. We solve for k. So k equals, what number is this? 5. 0.0183 s to -1. Again, this is 37.9 seconds. So just keep the unit for half-life what it was, but that's important because that determines our k. So that's our first step. And then our second step is just AT over A0 and equals negative k times any time. And we are trying to figure out, so this is where you have to be careful of the wording. And I mentioned this in class, but you see examples here and then on the worksheet. And then I think when we do the next part of the lecture today, this is how much decomposed. So that's how much is gone. The AT is always how much is left. And So that would be the 11.12%. So you just have to be careful with the wording. Decompose is when it's a regular chemical reaction. We're going to switch into nuclear chemistry today. And in nuclear chemistry, the word we'll be using is decay. So things decay, the nucleus decays, chemicals decompose. So we would do the natural log of, you assume A sub 0 is 100%. So you can do 11.12 over 100 or just 0.1112, and then divide by the K, 0.0183 per second, and you should get 120 seconds. And then you can also ponder, does it make sense? We can go through it for both of these. For this one, you can count your zeros, or you can say that's pretty much 60 seconds. And so natural log, we're solving for the fraction of AT over A0 equals negative KT. We're going to get rid of the natural log, so we're going to have e to that power. So e to the negative 0.0183 per second times the 60 seconds. So when you do these, just be careful that these two units, the K and the time units, they have to match so that they always cancel out. And you come out with 0.333. So you could have said 33.3%, or you could have just said roughly 1/3. It's really, some people like percents better, some people like fractions better, and doesn't make sense. So a comment to realize, this is a natural log decay, which means our graph has that curve to it. If you remember when you learned, probably not, but maybe somewhere back there in the recesses of your mind, it is not a linear decay, but our half-life, if a half-life is around 38 seconds, then 1 minute is less than 2 half-lives. Right? It's just a little bit less than that. So you can't mathematically do that, but so it should be less than a half, or 50%, but more than a quarter. So at the first half-life, it's 1/2. At the next half-life, it's 1/4. So that it makes sense. We're at a third, so it's somewhere in between there. We can't pinpoint exactly without doing the math like we did here. So in the explanations, you're just saying, yeah, that makes sense. If I asked you to explain for A, I want to go through that because it was a question major that you had asked me earlier. So here we're at 11%. And so the first half-life, so you would start, right, you're at 100%. And so you go through a half-life, you're at 50%. And then you're at 25%. I'm just doing this because when I count on fingers, it doesn't always work for people. And then you're at roughly 12% or 12.5% because it keeps cutting in half. And then you're around 6%. And then we go down, so 6.2 and then 3 point, blah, blah, blah. And so at 11%, we've gone more than 1, 2, 3 half-lives. So we've gone more than 3 half-lives. You didn't have to go that far, but that was just kind of an idea that keeps cutting. And so a half-life is 38 seconds. So it makes sense because it is more than 3 half-lives the time. So again, I'm just wanting you to get the idea. Okay, it's more, or it might have been if it was like 15%. Well, we didn't quite reach 3 half-lives yet. So it should be a little less than what 3 half-lives would be. Does that help? Like Major, you were asking me that question. And so it's more you're seeing in your mind, yeah, that makes sense. I'm not getting 500 seconds, which what makes sense for when we're around roughly 3 half-lives. Another way you can say it is we're at roughly 3 half-lives, right? Which would, we're roughly around 12%. So that makes sense. And again, if you got something like 500 seconds, that wouldn't make sense for this half-life if you've only gone through 3. So it's a way, the question is a way for me asking you, you should be going back and looking and saying, yeah, I'm in the right ballpark. Probably the biggest mistake, and for the people who are in my office hours, it was a question that everybody asked me, is just being careful with the wording for it when a percent is given. So this is telling you again how much decomposed. You're not going to use the 88.88. You want to be careful. If it tells you 88.88% remains, then that would be your AT. So again, how much is left is your AT. All right, and then the question at the bottom, because we've been doing lots of problem solving, it's more theoretical, so we just write the rate law. And so it tells us rate equals K, and it's second order for NO, so NO squared, and first order for bromine, so we would just say bromine. And then what's going to happen? So if the bromine is tripled, that's tripling to the first power, because that's what first order means, and NO is half, so it's 1/2 to the second power, or 1/4. So that means that my rate is going to be, K is constant, so my rate's now going to be at 3/4 of what it was, or at 75%. So that's all that's saying. So we're around 3/4. Any questions for that page? All right. And even though kinetics is really esoteric, so when I first started lecturing on it, it was probably really funky. It's not that bad. If you put the time in and just do the study sets and do the worksheets, then you're going to be golden. The radioactivity that we're getting into today, half of it is first order kinetics. So probably not half, 1/4 of it we've already done here. All right. So rate mechanisms. So adding up overall, we just want to cross out the pieces that are on opposite sides. So the NO3 is going to cross out, and that is an intermediate. So again, something that is produced and then used up is an intermediate. Now, something else does cross out, and that is there's an NO2 that you start with, and then you comes back out. So when you do your net, you're only going to have one NO2 plus the CO going to NO plus CO2. And again, on these, I'm okay with you leaving the states of matter off, or you can be really good and show them. The molecularity. So Christian, this is back to your question. I did ask here for each step, and this is how many collide. How many things collide is really what this is asking. And really, you're going to see two possibilities. Either one thing is decomposing, and that's unimolecular. We saw that in our notes on Tuesday. Or two things are colliding, even if it's two of the same, the NO2 with the NO2. This is always in the steps. You cannot do this for the overall, because the overall, we don't know what was colliding. The NO2 and the CO actually never actually collided. When they look at the mechanism, those two never came together. It was an NO2 with another NO2, and then an NO3 with the CO. So each step is bimolecular. So again, even if it's colliding with itself, that is bimolecular. So you can just say bi or bimolecular. And I usually say, what's the molecularity of the rate limiting step? And that is the slow step. And the rate equation is determined by the slow step. The other reason kinetics isn't so bad is because I cut out all the graphing stuff. That was more a kindness to myself and to all of you, because we're near the end and we're all tired of staring at a screen. And so so the slow step coefficients. So the coefficients equal the order. So we would just say rate equals K. So rate laws always say that, rate equals K. And then our reactant, so coefficients, reactant coefficients, sorry, is NO2, and there's two of them. So it's not 2 NO2, it's NO2 to the second power. So that is the order. So that's the rate law. We don't know that if, well, actually, here would be the question. What is the order? Because the order is always based on the reactants, and there are two reactants. So it's second order for NO2. So in a chart, Every time we double NO2, the rate is going to change by 4-fold. So my question is, what is the order in terms of CO? And how do you know? It's a really easy question. If it's not in the rate law, it must be what? It's a 0. So, and that's because it's part of the fast step. The fast steps, it's really, there's no comparison. The slow steps are taking their own sweet time, and the fast step is happening in the femtosecond. As soon as this NO3 is made, it's so reactive. It's not nitrate, it's missing an electron, and so it's going to react immediately. All right, so NO3 is the intermediate. Is there any questions on that? Again, this is like the esoteric stuff because it's very different from anything else we've ever done or ever will do again in this class. The diagrams, I have to tell you if it's exo or endo. So this is exothermic, which means you're starting out high and ending up low because you're losing heat. Your reactants, you can either show the overall reactants, or probably the better answer is, because we're going to show the steps, is that you would show your initial reactants were the 2 NO2s, and then your final product of the second step was the NO2 plus the CO2. But again, if you like to write the overall reactants, you can do that too. And the first step is rate limiting, so it's going to be the really high activation energy. I didn't indicate if the first step is exo or endo, so if I don't tell you that, you really have a choice. And then the second step is going to have a small hump. So it was a question I think Damon asked me during office hours. These are just really vague diagrams to say what's going on. The slow step, it's like climbing a mountain. It takes you longer to climb a big hill, much longer. You overemphasize it. So the slow step, which is almost always the first step, is the bigger hill. So from the starting, where you started, your reactants, to the top of the hill, that is your activation energy, so E sub A. And then we put a little 1 because it's the first hump or the first step. And then from that valley in between to the top of the next hill, that is your second activation energy. So it's going to be really tiny. It's really insignificant. The other piece is from where you started to where you end. That is your change, your delta H, which is negative here because it's exothermic. So that's just from last term. I just never showed you drawing exo versus endo because these diagrams are just one person's concept of how to draw them out. So something I did not ask you, but I'm going to go ahead and add it, is the catalyst. So if we added a catalyst, so the catalyst, right, you can do your cat. Rocky's sleeping. But the cat is going to lower the activation energy. That's actually a large conceptual question. That's what a catalyst does. That's how enzymes work in our body. For a lot of you are going into biology fields, and so when you take upper division biochemistry, they'll spend a whole term just on enzymology, and that's where you'll run into some of the kinetic stuff. But it would cut this down, so it's hard to see that line. But that's the idea of the cat, is going to cut the activation energy. It doesn't change the beginning and end point, but it cuts the hill out. So it's definitely much faster if we found a way around that hill. And it makes sense because the cat doesn't want to climb the whole hill. All right, number 12 is, again, just another way of asking the question. And chlorofluorocarbons were a huge problem. They're still up there in the atmosphere, so they're an amazing refrigerant. And they are a gas, so they float up, and once they get above the ozone layer, the UV light. So the ozone layer is protecting us from UV light. So the UV light actually cleaves off the chlorines and the fluorines. The good news is fluorine is so freaking reactive. Remember, fluorine's the most reactive. It reacts with anything it finds. Chlorine is a little bit more selective. And actually, once you get up there, most of what's up there is water. I mean, there's not a lot. I mean, you're way up high, but it's going to react with the water vapor that's up there. Chlorine wants ozone. It's like, I'm going to be more specific. And it finds ozone, and it steals an electron. And just because of how the winds in the polar air went, we ended up with a huge hole over the South Pole. There was actually a hole the past year or 2 years in our summer over the North Pole. It's just nobody lives there. But we banned them back, I think, in the 80s, and even stopped producing them because it was DuPont, of course. So the lower the K, the lower the rate. They are always proportional. So that is... a lot of you on your worksheets, I write comments to you, so please do make sure you look at those comments before our final celebration, which is like 2 weeks from now. I'm gone. I'm going camping. So we're all done in less than 2 weeks. Before the solar eclipse, we're going to all be done. Yeah. All right. So the lowest, the slowest is D. So the smallest K. K and rate are always proportional. All right, and then number 11 was just more mechanism stuff. And so more about the ozone. So this is what happens is ozone picks up the UV light and becomes O2 and O. Our overall, if we add up, these are called elementary steps, is the O is our intermediate, which makes sense because it's an O by itself. It's going to be highly reactive. So the O, gas. These are called, it's called a reactive oxygen species. That one's not made in our body. That would like kill us probably. We would end up with 2 ozones goes to 3 O2s. So we have 2 O3s and 3 O2s, and it is balanced. We have 6 oxygens on each side. So I'm going to add a step here. I didn't ask this question, the slow step. It was kind of back to something, a question earlier. This one, the slow step, is the second step. So if we wrote the rate law, we would say rate equals K times the ozone times the O. We have a problem, and this cannot be the rate law because you cannot have an intermediate in the rate law. So it requires us to do more algebra to get rid of the ozone, which requires what I teach you the very first day of Chem 223, which is July 26th. So I can do it. I can do the fancy math to get rid of the ozone. It's really not that hard. I just wanted to point that out. And it's kind of back to the question, Christian, that you had asked me. So it is possible that the second step could be the slower step, but technically our rate law would have to have we'd have to do some more math to get rid of the O. If this came up as a question for you, you guys would give me this as an answer and you would get full credit because that's as far as I've taught you. The other thing I wanted to mention, let's pretend, I don't remember if this is exo or endo, but let's pretend like it was endothermic. And this is kind of back to the question, Damon, that you asked me. Because my second step is the slow step, my first step would have a little hump and the second step would be the bigger hump. So that goes with question 9. And this reaction has 2 steps because there's 2 humps, like the camels in Asia, not the camels in Egypt. And is it exo or endo? This is endo. And then I ask a really good question. How about each step? So step 1 is endo. So we're starting here and ending here. So we're absorbing heat. So endo is it absorbs. But step 2 is exo. So if you look at step 2, it goes down. But overall, it is endo because we end up higher. And so that's actually a really good question. I had not been able to show that yet. If we look at how I drew my diagram up here, my first step was endo, and then my second step was exo. And so you might see a question that comes up in the future where I specify each step, that the step is endo, the step is exo, and that's how you can show it. And then the last one is, what is the rate limiting step and how do you know? It is step 1, and because it has the bigger hump, or hill, or mountain, or whatever you want to call it. So whichever has, or actually the better scientific way is it has the larger activation energy. So the activation energy would be from the start to the top of the hill, whereas this one would just have a little activation energy. So the larger activation energy. All right, questions? It's a little bit slower today.
Could you go over number 2? I think with Sensi. How did you get the order number for NO2?
So you can look, if you look at the first to the second, it's cut in half.
Oh, I'm sorry, on number 10C.
Oh, I thought you said 2. On 10C, it's because there's 2 NO2s.
So we would just add them together, but if they were different, that would be 1.
In all honesty, this should have been written as 2 NO2s go to NO plus NO3. I plagiarized this from a book, and I don't know why they wrote it like that. But so yeah, there are 2 of them. It's just another way of showing the coefficient. That's a really good question. You're okay now? Yeah. And that's why, like, when you take the celebration 3, I will be here. So if you have a question like that, you can always clarify. But I would more than likely write it like that. And also to comment on this is bimolecular because there's 2. Even though they're 2 of the same, it is still bimolecular. Anybody else? Questions?
So how come the rate equation is for NO2 is to the second order? But I thought
because there's 2 of them.
But I thought you can't have an intermediate in the equation.
NO2 is not an intermediate.
I thought one of them is because one's on both sides. No.
An intermediate, if you go back to how I defined it, is something that is made and then used up. NO2 is the opposite. NO2 is something that we're starting with and then it gets spit out at the end.
Oh, okay. That makes sense.
Now, if it's something that is not in the equation at all and it shows like that, that would be a catalyst. So a catalyst would be something like we'd say C here, and then it would come out. And actually, this is not a catalyst because it's one of the reactants, but a catalyst, if you look up the definition of a catalyst, and I realize I never gave you a really good definition, a catalyst is something that speeds up the reaction, but is not consumed by the reaction. So it is not in the net reaction. So it itself is not consumed or changed. And so the term is a chemistry term, but it is actually used a lot in other language, especially like in metaphysics, that they'll talk about somebody was a catalyst for your life or something. So they got you moving on a certain path, but they themselves may not have been changed. But that's not true because a human would always be changed by interactions with other humans. But so it's NO2 is not a catalyst and it's not an intermediate because it's in the overall. I guess would be the other way to think of it too, Christian. It's a really good question, but an intermediate has to be made in one step and then it will be used up later. not necessarily in the next step. Sometimes it's 2 steps later, because sometimes there's 2 intermediates that are made in the first step, and one gets used and then the other one gets used. Yeah. Good questions. Anybody else have a question? All right, stop.